The future space telescopes will blow our mind. Last Christmas, a rocket lifted off from French Guiana, carrying the largest space telescope ever made into space. Known as the James Webb Space Telescope, astronomers will use this scientific marvel to study everything from habitable exoplanets to the formation of the first galaxies. Webb is the first mega-telescope of this size to be launched into space, but it could also be the last. Indeed, with astronomers interested in ever larger telescopes, especially to answer the big question about the presence of alien life on extrasolar planets, the ability to build telescopes directly in space will become essential. As someone put it, assembling large structures in space is not really a matter of ifs and buts, it's just a matter of when. As we grow more ambitious in our desires to see further and more precisely in space, the need for larger and larger telescope mirrors becomes inevitable. The reason is very simple. Only with the collection of a large number of photons through a super large mirror, the quality of seeing can improve significantly. Large aperture telescopes benefit all astrophysics as well as planetary and Earth science. They provide unprecedented spatial resolution, spectral coverage, and signal-to-noise, advancing all of these science areas. The largest mirror in space is currently that of the Webb telescope, 6.5 meters. It will only become operational in a few months, but already astronomers and space scientists are pressing for larger mirrors to accomplish what the space telescopes of today cannot do. This is evident in the National Academies of Sciences decadal survey underway, which features 4 candidate flagship class observatories for the 2030s. 3 proposals call for telescope mirrors that are significantly larger than the Hubble's, and the most ambitious by far is Luvoir, which has been proposed at 15.1 meters or at 8 meters, or maybe something in between. A primary goal of Luvoir, and the reason for the large size of its mirrors, is that it will be looking for signs of biology on distant exoplanets, an extremely ambitious and challenging goal. The Luvoir team would have argued for an even larger telescope mirror around 20 meters, except that 15 meters is the maximum folded size that would fit into the storage space available on the super heavy lift rockets expected to be ready by the 2030s. This desire for larger and larger space telescopes has rekindled dormant but long-present interest in having an alternative to sending multi-billion-dollar payloads into space via one launch only. The alternative is in-space assembly, and NASA has shown increased interest in pushing the idea and technology forward. The fundamental reality behind the push for in-space assembly is easy to understand. Anything going to space must fit within the rocket taking it there. Even the very biggest, the mammoth 10-meter rocket fairing of NASA's still-in-development Space Launch System, would be unable to hold something like the International Space Station, or even the space agency's smaller Gateway, a moon-orbiting space station proposed for the Project Artemis in the 2020s. Launching such mega-projects piece by piece for orbital assembly by astronauts or robots is literally the only way to get them off the ground. And coincidentally, even through massive heavy-lift rockets such as the Space Launch System remain ruinously expensive, the mid-size rockets that could support orbital assembly with multiple launches are getting cheaper all the time. The forces demanding supersized space telescopes are straightforward too. The larger a telescope's light-collecting mirror is, the deeper and finer its cosmic gaze. Simply put, bigger is better when it comes to telescopes, especially ones with transformative objectives, such as tracking the coalescence of galaxies, stars, and planets throughout the universe's 13.8 billion-year history, learning the nature of dark matter and dark energy, and seeking out signs of life on habitable worlds orbiting other stars. Most of today's designs for space telescopes pursuing such alluring quarry cap out with mirrors as wide as 15 meters, but only because that is the approximate limit of what could be folded to fit within a heavy-lift rocket like the Space Launch System. Astronomers have long fantasized about building space observatories even bigger, with mirrors 30 meters wide or more, rivaling the sizes of ground-based telescopes already under construction for the 2020s. Assembled far above our planet's starlight-scattering atmosphere, these behemoths could perform feats the likes of which ground-based observatories can only dream. such as taking pictures of potentially Earth-like worlds around a huge sample of other stars to determine whether those worlds are actually habitable or even inhabited. If our own Earth is any example to go by, life is a planetary phenomenon that can transform the atmosphere and surface of its homeworld in clearly recognizable ways, provided that is, one has a telescope big enough to see such details across interstellar distances. A recent report from the National Academies of Sciences said NASA should take the lead on a major new space telescope that begins to approach that grand vision, something capable of surveying hundreds of nearby stars for snapshots of potential exo-Earths. That recommendation is reinforced by the core conclusion of another new Academy's report, which calls for the agency to make the search for alien life a more fundamental part of its future space exploration activities. These reports build on the growing consensus that our galaxy likely holds billions of potentially habitable worlds, courtesy of statistics from NASA's deceased Kepler Space Telescope and the space agency's newly launched Transiting Exoplanet Survey satellite. Whether viewed through the lens of scientific progress, technological capability, or the public interest, the case for building a life-finding space telescope is stronger than ever before and steadily strengthening. Sooner or later, it seems NASA will find itself tasked with making this longed-for giant leap in the search for life among the stars. How big such a telescope must be to offer a reasonable chance of success in that interstellar quest depends on life's still unknown cosmic prevalence. With a bit of luck, one with a 4-meter mirror might suffice to hit the jackpot, locating an inhabited exo-Earth around one of our Sun's nearest neighboring stars. But if the cosmos is less kind and the closest life-bearing worlds are much farther away, something in excess of the 15-meter limit imposed by near-future rockets could be necessary to sniff out any living planets within our solar system's corner of the galaxy. In short, in-space assembly may offer the only viable path to completing the millennia-long effort to end humanity's cosmic loneliness. Nick Siegler, chief technologist of NASA's Exoplanet Exploration Program, with other scientists proposed to NASA a study of robotic in-space assembly in 2018, and the idea was accepted. Siegler's study claims that for space telescopes larger than Luvoir, in-space assembly will probably be a necessity, because it's unlikely that heavy-lift rockets will be getting any bigger than what's being built now. And we have enough evidence to suggest there are benefits to assembling in space with smaller telescopes too. The final conclusion of the study, in fact, is that even with space telescopes in the range of mirrors of 5 to 7 meters and then above, planners should start thinking of robotic assembling in space to reduce a significant number of risks and maybe costs. The idea, however, was certainly not new. Even when scientists and engineers were contemplating for the first time the concept of Luvoir, they proposed that it be at least 18 meters in diameter and that it be assembly in space by astronauts. Different components of the observatory would be launched at different times, and then the astronauts would fit the pieces together. And that would be also a great way to train astronauts for the kind of work they will have to do in the future on Mars and in deep space. And it was perhaps the only way to get a really big telescope into space. The only difference was about who should be in charge of the assembly in space, human beings or robots. The answer came shortly. The effort to understand possibilities and challenges associated with in-space assembly led to a formal NASA study headed by Siegler, and the report released in 2018 concluded that while in-space assembly has a bright future, the idea of using astronauts to do the assembling rather than robots is not considered the way to go now. A decision that wanted to take into account the safety of astronauts forced to operate not in low orbit as happened, for example, on Hubble and the space station, but at 1.5 million kilometers from home in the region of Lagrange L2. But in particular, the study must answer the question, when is it advantageous to assemble space telescopes in space rather than to build them on the Earth and deploy them autonomously from individual launch vehicles? Well, from the point of view of risk reduction, the answer is definitively yes. With a telescopic monster like Webb, an explosion on the launch tower or a small inconvenience in the deployment of the mirror could easily turn the telescope into a $10 billion piece of space junk. But if the telescope is launched in pieces and assembled by robots, the errors become less devastating. If something goes wrong, you could simply send a spare part on the next rocket. To give a more complete answer, Ziegler and his colleagues also simulated the hypothetical assembly in space of a 20-meter telescope, about 3 times the size of the Webb telescope and twice the size of the Gran Telescopio Canarias, currently the largest optical telescope on Earth. This imaginary instrument could be used to search for exoplanets, which means it might be incredibly stable and precise. According to Ziegler, this was the hardest case possible. Things would be like this. First, NASA would send parts of the telescope on multiple rockets. The inaugural lot would bring the main platform for the construction of the telescope, some trusses disassembled for the support structure, and a pair of robotic arms. For a 20-meter telescope, 11 additional launches would deliver the remaining pieces of the telescope in capsules that attach to the telescope platform. At that point, the robotic arms can start to put everything together. It might sound like science fiction, but at the end of the day, we were doing something similar 20 years ago. Remember that the largest artifact made in space, the International Space Station, was assembled in orbit by astronauts aided by robotic arms, as well as Hubble during repair missions, and that even today robotic arms regularly guide cargo capsules to mooring with the space station and wander throughout its length to carry out repairs. Manual assembly by astronauts is highly cost inefficient or not feasible due to orbital constraints and increased radiation above the low orbit. However, autonomous robotic assembly systems could provide the means to build larger structures in space in the near future. Modularity is a key concept for such structures and also for reducing costs in new spacecraft designs. The advantage of the modular approach lies in the ability to generate a large number of unique resources from a small number of building blocks. Therefore, spacecraft can be easily adapted to particular use cases and could even be reconfigured during their lifetime using a robotic manipulation system. It's complicated, it's expensive, but it doesn't matter. It's just a matter of wanting to do it. The scientific community is sometimes its own worst enemy when it comes to understanding what it is that's possible, says Ken Sembach, director of the Space Telescope Science Institute. Some of us now have the preconceived idea that it is not possible to build another telescope that is bigger and yes, maybe more expensive than Webb. But I talk all the time to younger researchers, Congress, and the public, and they all ask, why aren't we thinking bigger? People want to support ambitious things, so it is possible provided there is a damn good reason to do it. And if NASA will decide to change gear or not, we will know in a short while, when it will have to choose the space telescope of the future to propose for funding by Congress. Will it be the 15.1-meter Luvoir A or the 8-meter Luvoir B? For the first time, we can say with a straight face that we're conceptually designing missions with reasonable expectations of finding life on planets outside the solar system. And to not do that when you have the opportunity to, well, that seems a little crazy. Doesn't it sound like that to you too?